What if the missing 85% of the universe was never missing at all? What if it was never there to find? Because the mistake wasn't in what we were searching for. It was in the one law of physics nobody thought to question, gravity itself. For decades, the standard explanation for why galaxies hold together has relied on dark matter, an invisible substance assumed to outweigh everything we can actually see. The reason we believe it exists comes down to a very specific problem. When astronomers measure how fast stars orbit around the edges of a galaxy, they move far too quickly. Under ordinary gravity, using only the visible mass we can detect, those outer stars should be flying off into space entirely. They aren't. So physicists added an invisible scaffolding of extra mass to make the math work, and called it dark matter. But in 1983, an Israeli physicist named Mordehai Milgrom proposed something far more radical. What if there is no missing mass at all? What if, instead, our understanding of gravity itself simply breaks down under specific conditions we had never properly tested? Here's the core idea, stripped down to its simplest form. Newton's law of gravity was built and tested using things nearby: planets, moons, falling objects, all of them experiencing relatively strong gravitational pull. Milgrom proposed that at extremely low accelerations, far weaker than anything in a physics classroom, far weaker than anything in our solar system, gravity might behave differently than Newton's equations predict. Not a small correction, a fundamentally different rule, one that only reveals itself at the outer edges of galaxies, exactly where the mismatch appears. This theory is called modified Newtonian dynamics, and here's what makes it genuinely difficult to dismiss. When you apply Milgrom's simple modification to a galaxy, the mismatched rotation speeds resolve themselves naturally. No invisible matter required, no fitting extra mass in by hand to make each individual galaxy work. And it does something even more impressive. It correctly predicts a precise relationship between a galaxy's brightness and its rotation speed, called the Tully-Fisher relation, a pattern so consistent across so many different galaxies that dark matter models still struggle to explain it as cleanly, decades later. For years, MOND remained a fringe idea, elegant on paper, but with one enormous, seemingly fatal problem. That problem had a name: the Bullet Cluster. Two massive galaxy clusters that collided millions of years ago, and in the aftermath, astronomers found something that seemed to settle the entire argument for good. Using X-rays, they could see where the actual visible matter, mostly hot gas, had piled up during the collision. Using gravitational lensing, they could map where the gravity itself was concentrated, and the two didn't match. The gravity was sitting somewhere the visible matter wasn't. Exactly what you'd expect if invisible dark matter had passed straight through the collision, while the visible gas collided and slowed down. For over 20 years, this single image was treated as the final word, taught in classrooms worldwide as definitive proof that dark matter had to be real, and that MOND simply could not explain it. In June 2026, that final word stopped being final. A team using new, far more precise star count data from the James Webb Space Telescope recalculated the actual distribution of visible mass across the bullet cluster, and found something startling. When measured correctly, the data lines up remarkably well with what MOND would predict, requiring either no additional dark matter at all, or at most, roughly half of what the standard model has assumed for 2 decades. The single piece of evidence considered most damaging to MOND may have been working against it because of an outdated calculation, not because the theory was actually wrong. Now, to be completely fair to both sides, because that's what this channel is built on, MOND is not free of problems either. It still struggles to fully explain the mass discrepancies found in some galaxy clusters, and a major recent test involving the orbits of distant binary star systems, expected to be one of the most decisive checks of the theory, has produced results that remain genuinely confusing rather than conclusive. Dark matter, meanwhile, still has no direct detection, not one single particle ever confirmed in a laboratory, despite decades of dedicated searching. So here is where actual science stands today. Not a settled answer, but a reopened question. One many physicists assumed had been closed for good 20 years ago. Two very different explanations for the exact same observations. One requiring an invisible substance we have never once detected directly. The other requiring us to admit that Newton's gravity, tested and trusted for over 3 centuries, might simply stop working exactly where we've never been able to properly check it. What do you think? Is the universe hiding an invisible substance we simply haven't found yet? Or has gravity itself been misunderstood since the day it was written down? Let me know in the comments. Subscribe, because next time we are covering the Vera Rubin Observatory's first complete dark matter map, the most detailed attempt ever made to finally settle this exact debate.